Hey there everybody, this is Mr. Sheline, and this is going to be the video lecture notes covering the Unit 7.2 notes, energy, and temperature. So we've been talking a whole lot about how energy temperature is related, what it can show, what it can do with states of matter. We've been looking at that, and so what we're going to be looking at now is just, we're introducing now the amount of energy that can be measured per the temperature that we're increasing. So first, we got to get into how we can use temperature to measure energy. So there's this thing that we call specific heat, and we label it with this little label of CS, okay, C sub S, okay. So specific heat is referring to the amount of energy needed in order to raise 1 gram of the substance, or I should say raise the temperature, that should say the temperature of 1 gram of a substance by 1 degree Celsius. So it's to say that, okay, I've got this thing, I've got a gram of it, it is 10 degrees, it's 10 degrees Celsius, and I put enough energy into it, and I'm recording how long it takes in order, and I'm recording how much energy I'm inputting it until it increases from 10 degrees to 11 degrees Celsius, as an example. I know it's kind of weird just verbally, but it'll make more sense as we practice this. So again, it's the amount of energy needed to raise the temperature of 1 gram of a particular substance by 1 degree Celsius. So the most common unit we use is lowercase, and I'm going to explain why it's lowercase. Lowercase calorie. Okay, now this is arguably one of the trickier things, and maybe the trickiest thing about this unit is remembering the difference between calorie and calorie. So we have lowercase calorie, which 1 lowercase calorie is the amount of heat needed to raise a temperature of 1 gram of, say, water by 1 degree Celsius. Now, or I shouldn't say, let's say water, it is. So 1 calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. So the measurements of calories are based upon how well and how fast, how it is that we can increase the temperature of water. Okay, why water? Because water is super easy to use. Water's everywhere, and it is just one of those, like I mentioned in class one day, it's a miracle molecule. So we use water to compare and to use as basically our tool of measurement here. Okay, so 1 calorie, we'd say one lowercase calorie is equal to the specific heat of water. Okay, now again, I mentioned that we have lowercase c calorie. Okay, and these calories it's an SI unit. We can use kilo, hecto, deca, mega. We can increase and decrease the range of our measurements by orders of 10. Okay, so for instance, 1,000 lowercase calories will be equal to 1 kilocalorie. Okay, or 1 kilocalories. Okay, so again, it's an SI unit. Okay, maybe make that note. SI unit. That's what this little spot right here just basically says, and what that's describing. Calories. Let's see. Calories. Oh my goodness. Calorie is an SI unit. Okay. Calorie is an SI unit. Now, I've been saying this thing about lowercase calorie because unfortunately we also use capital C, excuse the bell, we use a capital C to indicate kilocalories. So again, there's a difference between calories and calories. So here's what the difference is, and here maybe I'll zoom in a little bit on here. 1 kilocalorie, okay, so 1,000 calories is the same thing as 1 uppercase calorie. Okay, now notice we abbreviate uppercase calorie with uppercase CAL. which again, this is the same thing as this, which is the same thing as this. But for lowercase calories, the number, which again is the measurement of the energy needed to increase 1 gram of water by 1 degree Celsius. Okay. This guy here we abbreviate with lowercase c and then AL. So again, the tricky thing is to remember and to make sure that we understand the difference between uppercase calorie, lowercase calorie. And when I say that we have to understand that, I mean that when we start calculating this and we really get into specific heat, when we really get into converting calories to joules, which we'll get to in here in just a second, when we are doing that, we have to make sure that we are noting the proper amount of calories. So let's say for the sake of argument that you get an answer that's like, oh, well, there's 1,000 kilocalories. Let's just say it's kilocalories, and I tell you, give me the number of kilocalories in lowercase calories. Let's say that if you gave me this, so if you wrote this out, so if you were to say, oh, it's this many calories, that's an uppercase C. That's not correct. Okay, that is not correct at all. No. Okay, you have to know the difference between this versus this. So if you, I guess what I'm saying here is make sure, like, super duper exaggerate the uppercase C and uppercase calorie. Okay, when you're asked to do that or asked to answer in here, super duper exaggerate it so that there is no misunderstanding of what value or what units you're using, I should say, what unit you're using. That's a really, I know that seems kind of weird the way I've been phrasing this, but again, understand the difference between this versus this. This right here, there are 1,000 lowercase calories in 1 uppercase calorie. Okay, exactly what you wrote just up here. Okay. So understand the difference. Now, so calories are a lowercase calorie is the measurement of how much energy it takes in order to increase the temperature of 1 gram of water by 1 degree Celsius. And that's an SI unit. We also have an SI unit of how we measure energy, and we measure energy in what's referred to as a joule. Okay, Joule, and we abbreviate it with just a J. So this is how we measure energy. So 1 calorie, 1 lowercase calorie, is equal to 4.184 joules worth of energy. Okay. 1 uppercase calorie, or 1 kilocalorie, is equal to 4,184 joules. Okay. Again, measurement of water. How much? This is the amount of heat. Or the amount of heat energy that we have to put into water, or I should just say energy in general. This is the amount of energy we have to put into water in order to increase the temperature from, or to increase the temperature by 1 degree Celsius for 1 gram worth of water. God, it can be kind of confusing saying that, but again, we'll be practicing this. So then temperature. So before I get to temperature. So this is how we measure energy. This is how we measure the energy in the system. We have calories, which measures, again, for the 5th time, 1 lowercase calorie is equal to increasing the temperature of water by 1 degree Celsius when we are working with, or per 1 gram of water. 1 joule, or sorry, not 1 joule, but a joule is a measurement of how much energy is in a particular system. And 1 lowercase calorie is equal to 4.184 joules of worth of energy, while 1 uppercase C calorie, or 1 kilocalorie, is equal to 4,184 joules. Okay. Now, temperature. So where did temperature come from? Why do we care about temperature? What is it exactly? So I'll have a couple videos to show in class, so make sure you check Google Classroom. because I'll post along with this one. This video is going to go into like the Unit 7 notes section. On the stream, I'm going to post videos I'll post some videos about where did we get Fahrenheit, where did we get Celsius, and so watch those so you can have some context as to why it is that we use Celsius and why we use Fahrenheit. So what is temperature? Well, temperature is the average of the kinetic energy of all the particles within a substance. Okay, that's really all temperature is calculating here. It's not for us humans, yeah, sure, it's how hot or cold something is, but that's what we're feeling. That is a sensation that we feel in response to the environment, and more specifically, it's a response that is to help us survive. Other animals perceive temperature differently than we do, so it's not just a matter of what's hot and cold, because there are some animals that really don't feel hot in particular environments. There are some animals that don't feel cold like we do in particular environments because they're just built differently. So temperature is not, and maybe even make a note of that, it is not a measurement, of hot and cold. Because again, those two words, very subjective, meaning that it's very opinion-based. Because even there's some people that don't really feel cold the same way you do. I mean, shoot, there's like, what is it, some guy in Russia, I think it's Russia. And then there's also a guy like that lives in Alaska. The dude will like sit for hours in like a Speedo in iced over water, and then we'll be like, yo, hand me a popsicle, and he sits there in like negative, in like 30-degree water and be eating a popsicle, and he's like basically naked. There are people that feel temperature differently than you do, and vice versa. Okay, so temperature scales. So we use Fahrenheit for the most part in the U.S. And a couple other countries sort of kind of use Fahrenheit. We're really the only country in the world that still uses Fahrenheit. Almost everywhere else uses Celsius. Okay. It didn't used to be that way. We used to go by centigrade up until about, I think it was about 50s or 60s, and then we switched over to Fahrenheit. For the reason why we did that, I actually don't know why we did that. But anyway, so Fahrenheit is one of the earlier scales, and we'll have a video about this. It's still commonly used in non-scientific applications like weather and other applications as well. So this one we're very familiar with. Celsius, we probably have some experience, but for the most part have been ignoring it. Celsius is a scale based around the freezing and boiling points of water. And again, we'll have a video on this in class as well. Where the freezing point of water for Celsius is easy peasy, just 0 degrees. Boiling point of water is 100 degrees. And really that's how they came, for the most part, in kind of a certain way. That's how they came up with it. We'll have a bit more specifics on that in the video we're going to watch that may surprise you. Okay, and just remember Fahrenheit. For Fahrenheit, freezing, if we forgot, freezing is at 32 degrees Celsius, while boiling, boiling is at 212. At 212, 32 Fahrenheit, 212 Fahrenheit. Okay, and actually, that's off the top of my head. I better double check that. Hey, Google, what's the boiling point of water in Fahrenheit?
212 degrees Fahrenheit.
Dang, boy. So yeah, I guess I should know that. I'm a science teacher. But anyway, so the boiling point of water is at 212 Fahrenheit. Freezing's at 32 degrees Fahrenheit. Okay, and then we got this weird scale called Kelvin. Kelvin is technically the SI scale used to measure temperature, and it's based off the idea that there is like a temperature in which all motion stops. So this Kelvin is a measurement, like a more direct measurement, and here maybe we'll do this, more direct measurement of kinetic energy. Okay, so it's used to measure temperature in the idea that there's a certain point in which there has to be a certain point in which there's almost absolutely or almost all the energy has been taken out of a system, and you have absolutely no motion. It has to be there has to be a point that's like that. So Kelvin is again more about a direct measurement of how much kinetic energy is found within a system, and the range is just completely different. It's based upon, again, that concept of absolute zero. Okay. So what is absolute zero? Well, it's just the coldest possible temperature. Now, again, we've never been able to measure to this point. We don't have the tools necessary for it, but what we have done is that we can mathematically calculate that it must be possible at some point for something to reach absolute zero, to reach 0 Kelvin, based just upon trends on a graph. That it looks like, it looks like that, and I think I've shown this to you guys before. It's like, here's how, the temperature decreases, and then this is the last data point that we're able to measure. Past that, our tools can't do it. And they're like, okay, well, let's just use that slope and say like, and right there, that would be like somewhere right there would be absolute zero. Can't measure there, but we can mathematically, say it must be a thing. So it's at the point in which there's no energy at all and all movement has stopped. Okay, that's absolute zero. Now, we're going to practice conversions from different types of temperatures, because you're going to be in situations, and this is why we do this, is that you're going to be in situations where you may have tools that measure a particular temperature one particular way, and you need to be able to readjust if you then move to a different lab and now have different tools. Okay, or you're wanting to see what the difference is between them, because sometimes maybe there's some differences based upon the tool you're using. So here is the measurement, or here is the conversion to go from Celsius to Kelvin. Okay, so again, Celsius to Kelvin. So and maybe I'll do this, I'll even add some colors here to make it, and I'm gonna make that guy yellow over there. We'll make Kelvin green. God bless it. I just realized what I should have done is kept the colors up here. That kind of sucks, but whatever. We're gonna keep Fahrenheit green then. And we're going to make Kelvin pink. When it's really Celsius, that should be pink, so that's my bad. So anyway, if we're starting with Celsius, we're going from Celsius to Kelvin. This is what our equation would look like. So Kelvin, temperature of Kelvin is equal to whatever our temperature in Celsius is, plus 73.15 degrees. Now, if we're going from Kelvin to Celsius, we're going to say, well, Celsius is equal to whatever the measurement of Kelvin is minus 273.15. Okay, so easy peasy. So we can have a pretty solid conversion from Celsius to Kelvin. We have to do a little extra work if we're starting with Fahrenheit and have to go to Kelvin. So for Fahrenheit, if we're going from Fahrenheit to Celsius, it's just this. Celsius is equal to 5/9. I don't know why I'm getting this nasty glare right on that corner. No, get out. Okay, there we go. So it's going to be 5/9 times whatever the Fahrenheit measurement was minus 32. Okay. The best way that I think of this, so when I practice this, what I always remember, if I forget for a split second, I'm like, I don't have my conversion here with me. Which one's which? The best way that I think of it is that the 5/9 is a much smaller, it's a smaller ratio. We're also subtracting 32, and I know that the boiling point of water, the melting point of water is 32 degrees in Fahrenheit, but it's 0 degrees in Celsius. So I know that Fahrenheit is typically going to be larger than Celsius. So then I think I'm just using way smaller numbers. I'm also subtracting 32 when I'm going from Fahrenheit to Celsius. And then if I'm going from Celsius to Fahrenheit, it's just the opposite. I'm going to first add back the I'm going to add back the, oh my goodness. Sorry, I'm looking at this real quick. I don't think that's right, or I didn't put that in the notes correctly. Here, give me 1 second, guys. Or no, sorry, I said that wrong. Yeah, you're going to multiply, so think of it like this. You're going to first multiply. So here we're subtracting first and then multiplying by our fraction. Here we're multiplying first, then adding the 32. So it's 9 over 5 times Celsius, then plus the 32, when we go from Celsius to Fahrenheit. It seems pretty, I know I'm not asking you exactly to memorize this. It's not a bad idea to memorize it, or at least really practice to memorize it, because this will be given to you. Just it's in the case that you forgot. And I know we've got Google, whatever, but anyway, so this is how we convert from Celsius to Fahrenheit. Here's how we calculate Fahrenheit to Celsius, and then Kelvin to Celsius, then Celsius to Kelvin. So we'll be using this, we'll be practicing how we convert back and forth between these guys. And then the last little bit that I have for this set of notes is on the BIC, which is going to be a decent addition to the notes. It's going to be, it's for you guys to understand what the absolute zero is, what absolute zero is in terms of Fahrenheit, what absolute zero is in terms of Celsius, and then clearly for Kelvin. And it's just to show the discrepancies between them. Okay, so boiling point of water for Fahrenheit, 212 degrees Fahrenheit. For Celsius, it's 100 degrees. Kelvin, 373.15. Here's the freezing point, blah, blah, blah. Absolute zero, blah, blah, blah. Because we will be using these. We will be using these in order to when we're working with water, we're going to be using these to understand, energy lost, energy gained, or just the change of temperature, how that affects the energy that we're measuring in a system. We'll be using them when we get to enthalpy and also calorimetry. So anyway, that's pretty much it for the notes, guys. So that's all I have for you. If you still have any questions, make sure you ask. If not, I'll see you in the next one.